All right. Hi. Thanks for coming. Today, I wanted to talk about Swift on the server. There's a chance that maybe a lot of y'all don't even know that Swift is even possible on the server and web development in general. But this has technically been possible since December 2015 when Swift was open sourced. And although it was a little bit gnarly at the beginning, and now it's gotten a little bit better. And Swift is kind of an interesting choice for a language for server-side and web development because it's got a nice balance between friendliness and safety. So some of the most popular web languages are very well known for their friendliness. People love Ruby and Python, and some would say JavaScript, but they're not particularly safe in that they let you run code that would definitely fail at runtime. So Swift strikes this balance of being friendly in that it has a very familiar syntax, and it's got some nice tooling like with Swift playgrounds that are maybe a little bit nicer than REPLs and things like that. But also it can be quite safe. You can encode invariants of your problem into the type system so that you can have the compiler proving that impossible things are in fact impossible, like by the type system. So I want to kind of give a very broad stroke overview of what Swift can bring to web development. I think some of the stuff is pretty exciting. It's kind of some of the most exciting stuff I've worked on in a long time. And I think some of these things other frameworks can't really even touch. So there's a lot to cover, and this is going to go quite fast. But first, I want to say that all this work was done while working on a new project with my collaborator, Steven Sellis. It's a site called Point Free. It's a video series on functional programming and Swift and using Swift playgrounds. And we wanted to build the site in Swift using functional programming methods. And so we did everything from scratch, from first principles, just to kind of get a hold of what Swift could do. And everything I'm going to talk about today is open source. This is a GitHub organization. Anything that shows up in these slides is somewhere on this organization. But in fact, the entire website, the entire source code of the website is also open source. So you can see how we do every page, GitHub authentication, payments, everything. It's all there. So to start, let's kind of first define the layers of what makes a server framework, because I'm only interested really in one layer. So there's the low-level layer, and this is a part I'm not really interested in. And this handles socket connections and TCP and SSL and HTTP parsing. But its ultimate goal is to produce a URL request, which is a URL, a method, a post body, and some headers. And then this request gets handed off to a high-level framework, which is the part I am interested in. And the high level is responsible for interpreting the request, kind of picking it apart and matching on the URL and the method and the headers and all that stuff so that you can figure out a code execution path. It fetches data needed to build the response, and this is where you go into side effect land with Redis and Postgres and all that very complicated stuff. And then once the data is fetched, you render a view, and that can be HTML, XML, JSON. But the ultimate goal of this layer is to produce a URL response. And this is status code, response headers, and a response body. So from this perspective, it is not unreasonable to say that a web server is nothing more than a function from request to response. Just a function. And I think it can be highly illuminating to think of it in this way. And this is the level that I'm most interested in, where all my work has been, is how to break up this one gigantic function into as many small composable units as possible that are easily tested and understandable. And each unit should just be a pure function that composes into this larger function. And so we're going to take a lot of inspiration from functional programming. And these will be the three components that I'll be dissecting in this talk. All these pieces can be expressed as just simple, pure functions. So first, middleware. This is kind of the fundamental unit of composition in that request to response function we had. Naively, we may try to literally define it as a function that goes from URL request to URL response, but these functions don't compose because the output doesn't match the input. You can't just chain these things along. So better would be to have a single type that holds the request that came in and holds the response that will go out. And then each application of this function fills in a little bit of the response, like writes a status or adds a header or appends a little bit of data to the body. And these do compose, and so you can compose a bunch of them to get one gigantic function going from request to response. But even better would be to make con generic. So now it can hold kind of first-class data on the inside. So now with each pass of this generic going con A to con B, not only could you fill in a little bit of the response, but you could also transform the data A that came in to a whole new data type B. So if you just had a user ID, you could then make a database request and get an actual user from the user ID. But then a great way, like a mind-blowing way, is to add an additional type parameter that is not actually even used anywhere in the definition of con. And this is known as a phantom type. So here's the definition. It's just 3 fields, and you've got 2 type parameters, but notice the I doesn't show up anywhere. And it's only used to tag the type with some like type level information. Phantom types allow you to encode a kind of state machine into the types, and it can help you guard against doing invalid things at compile time. So what types I are we going to like plug into here? These are the states that we're going to go through to get from the request coming in to the response going out. These types have no runtime data or information or meaning. They're just compile like type level names to attach to a connection. So in the first step, you're only allowed to write the status code. That's all you're allowed to do. In the next step, you can only write headers. That's all you're allowed to do. And the next step, you can append data to the body of the response. And then finally here, you shouldn't be allowed to do anything except just send that response out to the server. So here's an example of what some of that middleware might look like. This is responsible for writing the status code. So if you give it a status integer, you'll get back middleware that transitions you from status open to headers open. Once you've made that transition in the state, you are no longer allowed to write the status. It is over, enforced by the compiler, never again. And this provides type level safety against a pretty terrible anti-pattern in web frameworks in which you can throw an exception at any layer in the framework, and it just continues bubbling up, and if you never catch it, it flips you to a 400 or a 500 or something like that. And here, you're not allowed to do that. You're not allowed to like make a database request way in some leaf view that fails, and then all of a sudden you get a 500 or a 404 or something like that. It's just not possible. So you could write, so once you're in the headers open state, now all you can do are write headers, and you can write as many as you want, and then you close the headers when you're done. Once you've closed the headers, you're not allowed to do it again. So this is where you gotta set your content type, set your cookies, everything else, because you can't do any more after this. And then finally, you need to write data to the response, and when you're in the data open state, you can just append data however you want, and then you end the whole thing. And then it's over. You're not allowed to change anything in the response. The only thing you can do is send it back to the server, to the browser. And then the beautiful thing is that since middleware is just functions, like we know how to compose these things because there was no layers of abstraction to like work through. It's just function composition. However, if you just do it like the normal way, you get this kind of tower where the innermost layer is the middleware we run first, and then we kind of go out in the layers. So you write the status, write a header, close headers, send data, and then end. This is not super readable, but we can do better. In Swift, you're allowed to define custom infix operators. And infix operators are a great way of flattening parentheses and flattening towers like that. So we define this arrow operator to aid in function composition. It just takes a function from A to B, a function from B to C, and you get a function from A to C where you just do G of F of A. And then using this operator, we can compose middleware easily. And this is like a web server now. You can construct a con value of a request coming in, pipe it through, you get a response out the other end. And because it's just pure functions, this is very easy to test. It's very easy to assert on the output of this. Okay, all right, that's middleware. There's a lot more to say, but that's like a fun preview. So next is routing, and then routing is really wonderful because it's notoriously tricky. There are a lot of approaches, but we're most interested in the approaches that leverage as much of the type system as possible. So let us define 2 goals for routing. Routing is just a transformation that takes like this nebulous URL request and produces a first-class value. But routing can fail because like a request can come in that we don't recognize, and so it should be optional. That's what the little question mark is. It helps us mark on the type level that a value is allowed to be nil or null. And if routing results in a nil value. That's a 404 page. So we want this transformation to be as type safe as possible. I don't have a great universal definition of what I mean by type safety. I can give a pretty good relative definition in which a construction is said to be type safe, more type safe than some other construction, if it can catch errors at compile time that the other one can only catch at runtime. Most of the routing solutions out there are not as safe as they could be. So to understand this, let's look at some approaches. Here's one approach, and it's kind of in the Sinatra style and Express style. You provide a string of the request you want to match, and you provide tokens for the little pieces you want to extract out of the route, and then inside the matching block, you get a dictionary of a string to string of all the parameters, and you can pluck out what you need. This is not type safe. All the parameters are stringly typed. So if you want to know what type ID was supposed to be, whether it be a string, an int, a UUID, or who knows, you have to trace through all the code and see how is it actually going to be used later. There's also no mechanism to tie what we're doing with those tokens in the Git with what we're doing with the tokens in the body of the block. We could rename tokens, add tokens, remove tokens. Those two things will inevitably get out of sync. So this is an example of something that you can make lots of edits that will result in runtime errors, but not compile time errors. Another goal of routing is for it to be invertible. And this is something that routing libraries typically omit. And that is, if you had a first class value, produce a request such that when you put that request through the router, you just get back to that value. This is useful for linking within your site. If you have a value like a user, you want to generate the URL that goes to that user's profile or something. And Rails has a wonderful story here, although it's untyped and dynamic, but you get all these little route helpers for every single route, and they generate URLs to your pages. However, because it's dynamic, it's very easy to get this wrong. And you don't know you got it wrong until runtime. All right, but at least Rails gave you something. And then, like, the amazing thing that I'm here to tell you is that it's possible to do this in a typed language like Swift. I think a lot of people would maybe assume that you kind of need a dynamic language to do stuff like that. Like, that's just how it is. And you give up the safety of a compiler so that you can do stuff like that. But it's built on a very old idea known as applicative parsing. And it's a very deep topic and very wonderful. And I'll just give a quick demo. Here we have a first-class type called route. And this is the value that we want to be able to construct from a request. It's an enum with a case for every single route in the site. An enum in Swift is also known as a sum type or a union type in other languages, and just allows us to express one option of many options. So you have the root route for just going to slash. You have an episodes route for going to slash episodes, and then with an optional order param that can only be ascending or descending. That's all we want to allow or recognize. We have an episode route for going to slash episode slash a string or an int, because you could have a human-friendly slug or the ID of the episode. And I want to stress that I'm not trying to show the happy path at all with this route. This is very much a real-world, unhappy, messy path in which I have optional values and user-provided values and enums, and I'm trying to give a good example here. And so how, when a request comes in, how do we pick it apart and convert it to one of these? Well, we create a value called a router that describes how we want to parse a request into each of those cases. And I will sympathize in that if I was not familiar with the applicative parsing style, I would think this looks like computer barf. It's a lot. But if you squint and give me the benefit of the doubt, you can see shapes in there that resemble the URLs that we're trying to match. So for the root, we just parse a get method and nothing else. For the episodes, we parse the get method and then slash episodes and then a query param named order that is of optional order type. And episode pages, you parse get slash episode slash a path param that is an int or a string, and then a query param ref that is an optional string. And then you take all those parsers and you jam them together into one big parser. So I'll again sympathize. It's not it can look quite frightening. However, I think everyone can learn how to manipulate these symbols, much in the way you manipulate pluses and multiplication and ands and ors. It's just algebra, and it can be nice. So then how do you use it? Well, you do router.matchRequest, and then you switch on it, and that destructures it into every single case that you want to recognize, and now you have an explicit code execution path for every single route. And why would you do this? Well, this is what the route looks like when it's compiling, nice and type checked. Here I added an extra query param t of type int, and the compiler stopped me saying, I don't understand this because your route has no int. So we're catching errors at compile time instead of at runtime. And then if you build a router in this manner, you get linking for free. You get to generate URLs and paths to any route you want. It's all checked by the compiler. It's impossible to generate an invalid URL because these two things were completely linked to each other. And that is the beauty of applicative parsing. And applicative parsing subsumes all ideas that we've ever known about parsing and routing. If you want to do namespaces and nesting, that's possible. If you want to handle multiple verbs like a Rails resource, you can do that. If you want responsive routes, you can do that and everything. I didn't set out to build any of these things, but it's all possible, and I haven't built most of these things. But it's focused on just small composable units that glue together in like new and exciting ways that you cannot possibly imagine when you first started. Okay, routing. It's type safe, extensible, composable. That's kind of nice. And now we come to view rendering, and this is maybe the funnest part. And this is where the Swift toolchain really shines. So view rendering is where we've already collected all of our data, and it's time to render out some JSON or HTML or whatever. A popular method is to use templates like mustache and handlebars. And they work by allowing you to write whatever HTML you want into a text file, and then you have little tokens you can interpolate values into. Templates are highly unsafe and way less expressive than just using a programming language, like even like Ruby or JavaScript, because templating languages are kind of a little ad hoc programming language, and they're not going to ever be as powerful as a fully fledged programming language. And so this is why we built a library for modeling HTML DOM with just like simple Swift types. And so this would be a document built with just structs and enums and arrays. And the wonderful thing is that you can transform these much like you would transform any data type. You can map over them and reduce them and filter them and do anything. They're very familiar if you're just familiar with any kind of data type. And then, of course, you can render it out into a nice, pretty format. And why would you do this? Well, we can encode HTML semantics into the types. So here we have something that's type checking because we have a list with a bunch of list items. But if we insert a p tag into a UL, that should be invalid, and the compiler is saying, I got an unexpected node in a child of a UL. So we're getting a little bit of type safety there. But of course, HTML is only half the story. There's CSS to worry about. But that can also be lifted to Swift. And then you get everything that Swift offers you without needing to build another ad hoc language like Sass or SCSS. And so here we have a little CSS fragment that's not even tied to a selector. We have like a base font style and a base heading style that just sets some nice defaults. And then here is where we glue it into some selectors. So here's where we bind styles to H1 and H2 selectors. Here we include the base style, so we just get that out of the way. And then here we do some specialized styles that is not shared across H1s and H2s. And then, of course, you can render it out, serve it up to a browser. But then the interesting thing is, because it's just Swift types, we have like the flexibility to use this anywhere we want. And there's no additional process or build systems to set up to do this. It's just Swift types. So we could take some of these styles and render them inline into an HTML tag, which is nice for like HTML or HTML emails and stuff like that. We could have a little style sheet that we include into the head, and then here, that's the Swift including styles into the head, and then this is how it would render out. We could also create a dedicated route to serve up the rendering of this style sheet and put a CDN in front of it so it hits the Swift code a single time and then never again. And we're able to do this because it was all already in Swift. We didn't need to have build tools to like glue together two separate systems. And it took very little work to do this because it's really Swift doing the heavy lifting here. I didn't build a language like a Sass or a Mustache to give me some of this stuff. I just used Swift to do it. And then testing. The best part is that all this stuff is very easy to test because it's just pure functions. You just pipe some data in, a cert one comes out the other side, but you can go a step further and you can do snapshot testing. So snapshot testing is where you record the output of a function to a file, and then later test will just assert the output of that function matches the file on disk. So you can snapshot the entire home page, and you just get broad coverage of everything that's happening on that page. Now, we do a lot of textual snapshotting, but you can also do screenshot testing. So we have over 100 screenshots of the site committed to the repo, and every time tests run, all 100 plus screenshots are generated and tested on pixel by pixel basis. So if a single pixel's off, it fails the entire build. And we test nearly every screen and every kind of state and edge case. So you got the home page on desktop. You have the home page on mobile. You've got the episode page when you're logged out. You have the episode page when you're logged in, and now the transcript came in, or logged in and a subscriber. You can snapshot little fragments like the nav on desktop, nav on mobile, nav when you're logged in, a light nav. Then you can also screenshot test emails. This is the email we send out. And so we also have a mechanism to take CSS and glue it into HTML DOM so we can inline everything. And now we get screenshot test coverage on emails. And so this is what an email goes out for notifying people of a new episode when you're not a subscriber. So you have a link to say subscribe or watch the preview. And then here, when you are a subscriber, it just says watch now. And these screenshots are so easy to run because we're running them on Mac with Xcode. So you just load up a little HTML fragment into what's known as a WK Web View, which is Apple's API to embed web views into applications. And this took very little work to get going. And then it just kind of keeps going. You can also develop entire web pages in a Swift playground. So you can live edit your page, and it's like live updating. This is the home page running in a Swift playground. Okay, so in conclusion, I think there's some things I learned while working on this stuff, and I think it'll be important to keep in mind as Swift on the server becomes more popular. Swift is, or soon will be, viable for web development. I think there's a few little things to work out. Leverage Swift's type system as much as possible so that runtime errors are just compile time errors. Keep as much of it in Swift as possible so that you don't need a lot of layers of build tools in order to get you to do like some basic things. Look to functional programming for inspiration. There's a lot of literature out there that's really accessible and wonderful. The router came from a paper I read that was published in 2010 called Invertible Syntax Descriptions, Unifying Parsing and Pretty Printing, which is what we needed. We needed a parse and print for the router. And then lastly, focus on small composable pieces. It should all just be functions. I never met a pure function I didn't like because they just are understandable, testable, and compose in new and exciting ways. So that's it. Thanks for letting me ramble like a madman for a moment. And again, on the GitHub organization, all the stuff is open source. Thanks.